Hello everyone, this is Professor Roman. Welcome to the fifth video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we're going to continue our discussion of one-to-one correspondences, especially those that involve infinite sets. In the previous section, I defined what it means to say that two sets have the same size or same cardinality. And I hope you agree that it sounds like a reasonable definition. In any case, it's universally accepted, so we have to live with it. And the definition that I gave in the last video applies to all sets. It didn't distinguish between finite and infinite sets, and that's how it should be. We don't want it to mean one thing for two finite sets to be the same size and something else for two infinite sets to be the same size. That would be, let's say, awkward at least. Now, given that this definition has been accepted, we also must accept whatever consequences follow from this definition. And so some of these consequences may seem a little, let's say, unusual, but we have to live with them. There is a one-to-one correspondence between the set n of natural numbers and the set z of integers. And I can give you a simple one-to-one correspondence. It begins like this. It might look a little confusing at first, but as we talk about it, you'll see it's not so bad. So the point here is that on the left appears every natural number exactly once, and on the right appears every integer exactly once. And they are organized on the right by absolute value, increasing absolute value. So for a given absolute value, there are two integers that have that absolute value. Negative 1 and 1 have absolute value 1, negative 2 and 2 have absolute value 2, and so on. It should be pretty clear from this pattern that we have a one-to-one correspondence between the natural numbers and the integers. And so these two sets have the same cardinality. If we want to take a little closer look at this correspondence and produce a formula for it, we can do that. And the easiest way to see what's going on is to split the correspondence into two parts. So on the left here, I have all of the even natural numbers, and they are paired with the positive or non-negative integers. On the right, the odd natural numbers are paired with the negative negative non-zero integers. Okay, so I just split these. I took every other one for the left side and every other one for the right side. But now it should be pretty easy to produce a formula. On the left here, even natural numbers are paired with the number you get by dividing by 2. Okay. Each of these is half the one on the left side. For the odd natural numbers, it takes a minute to sort this out, but if you add 1 to each of these numbers, divide by 2, and then switch the sign, you will get these numbers. So that looks like this. And we can put those together in one formula. You could actually improve on this a little bit if you use the greatest integer function, but it's not worth the trouble, I don't think. Now, so this is about the most concise formula we're going to have for this one-to-one correspondence, but it does not prove that this is a one-to-one correspondence. And so if you insist, I will do that for you. And the first step is, I think, to write this pairing in function notation. So what we need to do is show that this function is a bijection. It's surjective and injective. As to surjectivity, if we take an integer that is non-negative, call it z, then f of 2z, since 2z is even, is 2z divided by 2, which is z. So all the non-negative integers are in the image of this function. For a negative integer, if we form 2 times the absolute value of z minus 1, that is odd. So according to the formula here, the value of f on that odd number looks like this, which simplifies to z. So the negative integers are also in the image of this function, and so the function is surjective. As to injectivity, there's 2 ways we can do this. One way is to take 2 natural numbers that are different and an m, and we need to show that their function values are different. Well, if n and m are even, both of them, then the fact that n and m are different implies that n over 2 and m over 2 are different. In other words, f of n is not equal to f of m. Similar analogous argument when they're both odd. And finally, if m and n have opposite parity, then their function values have opposite signs, and so they can't be equal. So f is both surjective and injective, and therefore is a bijection. Let's talk now about describing one-to-one correspondences between a set A and the set of natural numbers. A set A is in one-to-one correspondence with the natural numbers if and only if the elements of A can be written as an infinite list, or more formally called an infinite sequence, and with no duplicates. So each element of A appears exactly once in the sequence. It's important that this list be infinite, so this list does not terminate, otherwise we have a finite set. And that's what the ellipsis here, this 3-dot symbol is intended to convey, that this goes on forever. In the context that we are working in, that is to say, the sizes of sets and one-to-one correspondences, we can think of this sequence as a shorthand for writing this, which is the pairing that we're a complete pairing of the natural numbers with the set A. Or we can think of it as another way to describe a function. So as long as the sequence is infinite, and as long as each element of A appears exactly once, this tells us that the set A is equipolant to the natural numbers. Now, sometimes we're going to write this sequence and we're not going to have subscripts, as we'll do in the next example. So if you don't see the natural numbers, they're still behind the scenes. So instead of going through all of this rather lengthy example here, which was fine to do, instead of writing this as our one-to-one correspondence, we could have simply done this. The infinite list, 0, -1, 1, -2, 2, and so on, includes each integer exactly once. And so the set Z of integers is equipolant to the natural numbers. That is sufficient. It's not as formal as the version I did before because I didn't produce a formula and I didn't prove that it was a one-to-one correspondence. But this is commonly the way these sorts of problems are done. Okay. Here's another example. There is a one-to-one correspondence between the set n of natural numbers and the set n cross n of all ordered pairs of natural numbers. And to show this, we'll construct an infinite list. And it's sometimes better to break it up into several rows. It makes it easier to see what's going on. To try to stick all of this in one line, it would be really awkward. So the sequence begins with this ordered pair, 0, 0, and then 1, 0, 0, 1, 2, 0, 1, 1, 0, 2. You might see the pattern already. The nth row, where n starts at 0, so this is in the 0th row, this is in the first row, and so on. The nth row starts with the ordered pair 0n, n0, okay? And the other entries in the row are obtained by subtracting 1 from the first component and adding 1 to the second component. So the nth row here contains all the ordered pairs whose components sum to n. And with that in mind, it becomes fairly clear, I think, that this list includes every ordered pair exactly once. Every ordered pair has a certain sum of components. You'll find that ordered pair in the relevant row of this list. So we can conclude that the Cartesian product n cross n is equipolant just to n itself. We can even allow duplicates in an infinite list, and that happens, as we'll see an example in a minute, provided that after removing or just ignoring the duplicates, we still have an infinite list of the elements of the set A. And it will now be unique because we deliberately removed any duplicates. So let's take a look at an example. There's a one-to-one correspondence between the set n of natural numbers and the set q plus of all non-negative rational numbers. So here is an infinite list of rational numbers, non-negative rational numbers, organized in separate rows based on the value of the sum of the numerator and the denominator. That's somewhat artificial, but it works. So if the sum is 1, you have no choice. It has to be 0 over 1. 1 over 0 doesn't make sense. If the sum is 2, it's going to be 0 over 2 or 1 over 1. In general, when the sum is k, we start with 0 over k, and then we add 1 to the numerator, subtract 1 from the denominator, and we'll get 1 over k minus 1, then 2 over k, did I say that right? Yeah, 2 over k minus 2, and so on, all the way to k minus 1 over 1. Okay. Now, this list contains every non-negative rational number, n over m, but with a lot of duplicates. So if you look, for example, at the first entry in each row, all of these are equal to 0. So that's infinitely many duplicates of 0. But we can remove these duplicates or ignore them. And what will we have left? Still an infinite list of the elements of Q plus, now with no duplicates. When you remove duplicates, you don't reduce the size of the underlying set. You're throwing away copies. So you still have, you could say, the original of each element. All we need to make sure is that this deduped list is in fact still infinite. Conceivably, we could have thrown away so much stuff that the list is now finite. But that's not the case, because these elements, 1 over 1, 1 over 2, 1 over 3, these rational numbers are still in the list, and there are infinitely many of them. So we still have an infinite list of all of the non-negative rational numbers appearing, each one appearing exactly once. And so we have this. And I'm going to leave it to you to ponder how you would show that the set of non-negative rational numbers is the same cardinality as the set of all rational numbers. And so Q and N are equipolant. Okay. And we now know that N, Z, and Q all have the same size. And we might be tempted to conclude that maybe this is evidence that all infinite sets have the same size, which used to be the thinking among mathematicians. I'll talk about that some more later. But that's not the case. And to see why that's not the case, let's look at this example. We can show that the set, which I called S, of all real numbers strictly between 0 and 1 is not the same size as the set of natural numbers. This is also called the open interval from 0 to 1, the set of all real numbers strictly between 0 and 1. This is a little bit dangerous notation because it also stands for an ordered pair containing just 0 and 1, but in this context, it's the set of all real numbers between 0 and 1. So what we want to do is show that there cannot be a one-to-one correspondence between N and S. And the way to do that is to show that given any pairing, I didn't say complete pairing, just pairing, of the elements of N and S, in which every natural number appears exactly once on the left, and we don't know what these are, except they come from the set S. No matter how you try to do this, there will always be some real number in S that is missing from the right side. And so there is no complete pairing of these two sets. There's no one-to-one correspondence between the two sets. Now, to describe the idea, I'm going to use an example, but you, I think, will see that there's nothing special about this example, and this would work no matter how you tried to construct a pairing. So here is my example. I just made up these decimal numbers. Real numbers between 0 and 1 exclusive are decimals that have a 0 in front of the decimal point. I didn't put the 0 in here. Okay. One thing, however, we do need to do for this description is if a decimal terminates, like if one of these is 1/2, it would be simply 0.5, then we assume that we follow that by infinitely many zeros, so 0.5000 forever. That way, all of these are infinitely long decimals. Okay, doesn't change their value, but we're going to need that, and you'll see why in a minute. Now, the next thing to do is to identify, and I did this in red, the first digit from the first pairing, the right side of the first pairing, R1, the second digit from R2, the third digit from R3, fourth digit from R4, and so on. And this will go on forever. And now you see why I want these decimals to extend. Next, we take these red digits and we form a new decimal. Then we can construct the missing real number, which I called x, missing from the right side of the list, by deliberately changing each digit in this number r. And there's a lot of ways you can do that, but here's one way. If a digit in r is not equal to 5, then set the corresponding digit in x to be 5. So that's a deliberate change from a non-5 to a 5. If a digit in r is a 5, we'll change it to a 3. It could have changed it to a 2 or a 4, it doesn't matter. You have to change all the 5s to the same number. So we're changing them to 3. So from here, we get this. This is not on the list. Why not? Well, x is not equal to r1 because the first digits don't match. Deliberately. X is not equal to r2 because the second digits don't match. X is not equal to R3 because the third digits don't match, and I think you get the idea. X is nowhere on the list. So the pairing cannot be complete. It's not a one-to-one correspondence. And since I think it's pretty clear this works no matter how you try to set up the pairing, we have shown that there is no one-to-one correspondence between n and s, and so they do not have the same size. Well, this result is quite remarkable, really. It shows that not all infinite sets have the same size. It's not very difficult to show that this open interval S has the same size as the set of all real numbers, and I left that for the exercises, and I gave you a hint. Without the hint, it might take you a little while, it could be tricky. With the hint, it's a whole lot simpler. Okay. So we can say then that these sets, well, this is the even natural numbers, the natural numbers, the rational numbers, the integers, they all have the same size, but the real numbers have a different size. And it's time now to get more specific. We've discussed up to now only what it means to say that two sets have the same size. We haven't considered what it might mean to say one infinite set is larger or smaller than another. And so let's take a look at the definition. A set B is larger or has larger size or has larger cardinality than a set A, and we'll denote it by writing this, cardinality of A less than cardinality of B, if two conditions hold. First, A and B do not have the same size. That's an obvious condition. In other words, there's no one-to-one correspondence between the two sets. And second, there is a one-to-one correspondence between the set A and some proper subset of B. I called it S. Okay. And of course, if B is larger than A, we'll say that A is smaller than B. I suppose you might be wondering why we have two conditions. Isn't the second condition enough? If A is in one-to-one correspondence with some proper subset of B, shouldn't it be smaller? Well, we've already seen that's not going to work. The natural numbers form a proper subset of the integers, so they're certainly in one-to-one correspondence with themselves. And so part 2 is satisfied by the sets n and z, but we've already seen that n and z have the same size. So we do need both conditions for infinite sets. For finite sets, we don't. But to be consistent and not have to split this into two separate cases, we need both conditions in the definition. Something we can say, and I left the proof for you, if a set A is in one-to-one correspondence with a subset, proper or otherwise, of B, then either the two sets have the same cardinality or the cardinality of A is smaller than that of B. Okay. And then we'll express those two possibilities in the usual way with a less than or equal to sign. So, according to the previous definition, the set R of real numbers is larger than the set N of natural numbers, and I'll let you fill in the details on that. And so now we have this. N, Z, Q. I left out E because it's kind of not that interesting. N, Z, Q, equipolant, all have the same size. R is actually bigger. Well, this naturally leads us to wonder if there are any other infinite sets whose cardinalities are different from N and R. Are there only two sizes of infinite sets, or are there more sizes? Well, it was our friend Georg Cantor who showed that the power set of a set is always larger than the set itself. This is pretty easy to see for finite sets. In fact, when we talk about counting techniques, we're going to get into that detail. If a finite set has size n, its power set has size 2 to the n. So will be also finite, but larger, strictly larger than the original set. For infinite sets, this is also true, but takes more work. Cantor's theorem. The power set, P of S, of any set S is larger than the set S. There are infinitely many different sizes of infinite sets. And in particular, we start with the natural numbers. Its power set is larger than n. And if we take the power set of the power set, we'll get a still larger set, and so on. Part 2 actually follows directly from part 1. I'll let you deal with that. So let's look at the proof of part 1. If S is empty, then the power set of S is the singleton set containing the empty set, and so that's larger than S by 1. So we can assume that S is not empty. Now, it's easy to find a one-to-one correspondence between S and a proper subset of P of S, the power set. All we have to do is match an element from S with a singleton subset. This is clearly a one-to-one correspondence between S and the subset of all singleton sets taken from S. So that's part 2 of the definition of one set being larger than the other. But we still have to show that S and its power set don't have the same size. And we'll do this by showing that for any pairing of S and P of S that uses all the elements of S exactly once, say on the left, there's an element of the power set that's going to be missing from the right side of the pairing. This is similar to the argument we made to show that the set of real numbers between 0 and 1 is larger than n. It's the same idea, to show that there's no one-to-one correspondence. So suppose we have a one-to-one correspondence from S to the power set of S. So each element little s in the set S is paired with a subset which I'll write as X sub S. So we have this pairing as little s ranges over the entire set, capital S. What I'd like to do is produce a contradiction to show that there is no such one-to-one correspondence. Well, I'm going to refer to X sub S as the paired subset to S. We can classify the elements of the set S into 2 types, according as whether the element little s belongs to its paired subset or does not belong to its paired subset. It could be either one. All we know is that little s is paired with some subset of capital S. Whether little s is in capital S or not, we don't know, so we have to consider the 2 possibilities. Now, Cantor showed that the set, which I'll call T, of all elements of S that are not contained in their paired subset, the set of all these elements, little s, which I call T, is missing from the right-hand side. If it should appear on the right-hand side, there would be a pairing of this form. Some little s would pair with T. Well, let's look at S and T as far as membership is concerned. If little s belongs to T, then by definition of T, S is not contained in its paired subset, but that's T. So if S is in T, S is not in T. If S is not in T, then by definition of T, S is contained in its paired subset, so S is in T. So we have a contradiction, and you may recognize this argument. We've used it before, not in this video, but in a previous video. The only way to avoid this contradiction is to conclude that there is no one-to-one correspondence between S and its power set. So they don't have the same size, and we have shown that this is the case. Well, Cantor's theorem has very profound consequences. Before Cantor's time, it was generally believed that there was only one infinity. And I'm going to talk about that a little bit later, and what, for example, Aristotle had to say about infinity. And it's quite remarkable and very confusing. But now we see that there are, in fact, infinitely many different sizes of infinite sets. We already know there are infinitely many different sizes of finite sets. Now we know the same is true for infinite sets. What is the smallest size of infinite sets? You probably can guess, but guessing's not good enough. So here's the theorem. Every infinite set A contains a subset that is equipolant to the natural numbers. Therefore, the set N has the smallest cardinality among infinite sets. So if A is an infinite set, then the cardinality of N is less than or equal to the cardinality of A. And as to proof, if A is an infinite set, it's non-empty. We can choose an element, little a1, from A. If we take it out of A, we get another set, capital A1. That's non-empty, because otherwise, if it were empty, A would have just been this singleton set, and it would have been finite. We're assuming A is infinite. So we can do this again with the set A1 and choose an element A2, and we pull that out. We've pulled out both A1 and A2 from capital A, still non-empty. We can keep pulling out, in fact, an entire infinite sequence of distinct elements from A. So N is in one-to-one correspondence with that subset of elements. So every infinite set contains a subset that is equipolant to the natural numbers. In fact, lots of subsets. And then 2 will follow from 1. So the natural numbers, its cardinality is the smallest cardinality among infinite sets. There is a bit of notation associated with the cardinalities of infinite sets. Take a look at this symbol. I've made it larger than normal so you could see some of the details. It's a beautiful looking symbol. It's pronounced Aleph, A-L-E-P-H. It's the first letter of several Semitic alphabets: Phoenician, Hebrew, Aramaic, Syriac, Arabic, and others, I guess. And the cardinality of the natural numbers, the smallest cardinality, is often denoted by Aleph naught. You could say Aleph sub 0, but almost everybody says Aleph naught. So we have this formula. And I'll bet none of your friends would recognize this unless they studied mathematics. So Aleph naught is the smallest infinite cardinal. The cardinality of the set R of real numbers we've already seen is larger than Aleph naught. It is denoted by the letter C and called the power of the continuum. So this is what it would look like in symbols. And the reason for this terminology is that the real line is sometimes called the continuum, and the cardinality of a set is sometimes referred to as the power of that set. These terms are, I think, a little bit old-fashioned. They're older terms, but the term power of the continuum has stuck with us. So we can now write this equation, or inequality, among cardinal numbers. Sets of cardinality all if not, the ones that are equipolant to the natural numbers, are said to be countable or denumerable, because any bijection from n to s in effect is counting or enumerating the elements of the set S. And we can also count elements of any finite set, so they're also countable or denumerable. And here's the complete picture on the definitions here. Any set that has cardinality all if not is countably infinite. It's infinite, but it is countable, unlike the real numbers, which is infinite but not countable. Any set that is either finite or countably infinite is just called countable or denumerable. A set that's not countable is said to be uncountable. So I know it's a lot of terminology, but you have to learn it. Okay. The sets n, q, and z are countably infinite. They're countable also, but countably infinite is more specific, because countable includes not only the countably infinite sets, but also the finite sets. The set R is uncountable. And the set I of irrational numbers is also uncountable. It has the same size as R, but I'm not going to prove this. It's not terribly difficult, but it's taking us too far afield, I think. The remarkable thing here, if you think about it, is that the real numbers are not countable. In other words, there's no way, there's so many real numbers that you can't enumerate them. You can't write a list that will contain all the real numbers. There's just too many. And the same applies to the set of irrational numbers. There are too many. If you think about the real line, you may know that between any two distinct elements or points on the real line, there is a rational number in between. So the rational numbers are spread uniformly throughout the real line. No gaps. There's no interval that doesn't reduce to a point, no non-trivial interval that has no rational numbers. There are rational numbers inside every interval. And yet, despite what that geometry might lead you to think, there are far fewer rational numbers than there are irrational numbers. So that's weird, and that's one of the surprises from the definition that we've been using for cardinality. Well, I think we've probably done enough in this video. I'd like to continue, but I'll pick it up in the next video from this point on. So thank you for watching this video. I hope you found it interesting or at least stimulating, and I hope to see you in the next video.